Instant DBMS Assignment Help. For any assignment-related queries, call us at +1 678 648 4277. You can mail us at info@databasehomeworkhelp.com or reach us at https://www.databasehomeworkhelp.com. Part 1 Warm-up 1. We studied 3 disk-based access methods in class: heap files, B+trees, and hash files built via extensible hashing. Suppose you have a table A with A records in it and a table B with B records in it, where A less than B. Each table has F yields, F1 and F2. For each of the following query workloads, describe which access methods would be best suited to that workload, including whether any indices should be clustered, primary, or unclustered, secondary. You may assume that sequential disk I/O is 10 times more efficient than random I/O. Justify each answer with a short sentence or analytical argument. You may disregard insertion and deletion costs. A sequential scan of all elements of A. The best choice of access method is a heap file on A, since the pages need to be scanned in no particular order. Although other clustered access methods can also be used to scan relatively efficiently, pages are usually not arrayed sequentially and there is some space overhead due to key values and slash or pointers. B. A join of A and B of the form A.F1 equals B.F1. There are several roughly equivalent ways to answer this question. A merge join on 2 sorted heap files, or between 2 B+trees would likely be most efficient, since we are unlikely to have to read in any page of either relation more than once. The only way this could happen is if there are many, more than will fit in meme or y, duplicates of one particular value. Alternatively, we could build a hash file on B.F1 and a heap file on A, and perform an index nested loops join with B as the inner relation, which would be efficient if most or all pages of the hash file fit into memory databasehomeworkhelp.com. C. 50% range queries of the form A.F1k on A, where k is a constant, and 50% joins of the form A.F1 equals B.F1. By building a clustered B tree on A.F1, we can efficiently answer the range queries. For the joins, we can use a simple heap file on B and perform index nested loops joins with A as the inner relation. Alternatively, we could use a clustered B tree or a clustered hash file on B.F2 and perform merged joins or a nested loops join with B as the inner relation, as in the previous question. D. 90% range queries of the form A.F1k on A, and 10% joins of the form A.F2 equals B.F2. A clustered B+tree on A.F1 will allow us to answer range queries efficiently. With a B+tree or hash file on B.F2, we can perform an index nested loops join with B as the inner, using the link pointers in the B+tree on A to sequentially scan it as the outer. Note that in this approach we aren't accessing A.F2 in sorted order, meaning that we may have to read some pages of B multiple times, unless the entire relation fits in meme or y, and we won't access B in sorted order. Assuming that we are allowed only one clustered index per relation, the other viable alternative is to keep a second RY B+tree on A.F2, and perform a merged join. This requires random access into the pages of A, which will be inefficient as well. E. 33% joins of the form A.F1 B.F1, 33% sequential scans of B, and 33% lookups of the form B.F2 equals K. We can use a clustered B+tree on A.F1 and B.F1 to compute the joins and sequential scans reasonably efficiently. An secondary hash index on B.F2 will allow us to compute the lookups quickly. Databasehomeworkhelp.com. Part 2. Bob is a vacuum cleaner salesman. He has decided to store information about his clients and sales in a database. He wants to keep the following information. A. For each customer, he wants to store his or her name, address, and the sales price of all the vacuums he or she has purchased, some customers own multiple vacuums, and one crazy old man even owns 3 of the same type of vacuum. Bob sells his vacuums for different prices to different customers. B. Each vacuum model has a different horsepower rating which Bob also wants to store. C. As a way to increase his profit margin, Bob tries to get customers to buy a 1-year service contract with the vacuums he sells. Bob visits customers who have bought a service contract and maintains their vacuum for them. Thus, for each sale, Bob wants to keep track of the sales price and the type of service contract, if any, attached to the sale. D. Each type of service contract has a service frequency associated with it, which Bob wants to store in the database. E. For all service contracts, Bob wants to store the last time the customer's vacuum was serviced. DatabaseHomeworkHelp.com. Bob, knowing he's not being the brightest bulb on the tree, is concerned that he won't be able to write complex queries that combine readings from multiple tables together to get information about his customers and their vacuums. Thus, he proposes to store his database in a single table, reasoning that this way he only has to store 1 record per vacuum he sells, and it will be very easy for him to look up information about his business. His schema is as follows. Vacuums, SID name, city, street, no, model, no, HP, price, contract type, SVC frequency, last SVC. This representation works fine for a few months, but as Bob's customer base grows, he finds it is very hard to maintain this database, particularly as customers retire their old vacuums in favor of new models with new service contracts. He hires you to help him fix his database system. 2. Derive a set of non-trivial functional dependencies for this database from Bob's requirements given above. Assuming that no customer buys the same model of vacuum twice, reasonable functional dependencies would be SID-name, city, street, no contract _ type SVC _ frequency model _ no HP SID, model _ no price, contract _ type, last _ SVC DatabaseHomeworkHelp.com. In reality, to make this a good schema and support the possibility that a particular customer might buy the same kind of vacuum twice, we should introduce a transaction ID key for each purchase, which would change the last dependency above to something like TID-SID model _ no, price, contract _ type, last _ SVC. 3. List 3 update, insertion, or deletion anomalies that Bob might encounter using the schema he has proposed. Every time a particular model of vacuum is purchased, Bob must enter the horsepower information. If he does this incorrectly, the same model of vacuum can be listed with 2 different horsepowers. Every time a contract of a particular type is purchased, the service frequency is entered in the new record. He could do this incorrectly, causing 2 records with the same service contract type to have different service frequencies. When a customer changes his or her address or name, Bob might have to change that address, name, in multiple records. If he doesn't do this, there will be an update anomaly. There are several possible variants on these basic anomalies. DatabaseHomeworkHelp.com. 4. Use your functional dependencies to derive a schema in BCNF for Bob's database. Assuming the use of the TID field above. Customer, SID, name, city, street, no, contracts, contract _ type SVC _ frequency, vacuums, model _ no HP, sales, TID SID model _ no, price, contract _ type, last _ SVC. Does your schema preserve all of the functional dependencies you began with? Does it address all of the anomalies you listed above? Yes, and yes. 5. Suppose that Bob wants to find the names and addresses of all of the customers who live on Main Street whose vacuums are due for service. Suppose that 75% of customers own service contracts, 25% of them live on Main Street, and 10% of the service contracts, irrespective of contract type, are due for service. Assume there is no relationship between where a customer lives, the likelihood that he or she purchases a service contract, or the likelihood that a particular